Hello everyone. Hope you are doing very well. Today, as you all know, that we are going to cover our chapter 6, that is Haloalkanes and Haloarenes in detail, right? So let's begin our today's topic, that is NCERT chapter 6, Haloalkanes and Haloarenes, theory part 1. And today we are going to cover the NCERT section 6.1 to 6.1.3. Let's see. This is our disclaimer. Objective. So, what is the objective of today's lecture? After attending this lecture, you will be able to name haloalkanes and haloarenes according to the IUPAC system of nomenclature from their given structure. Okay. So, today we are going to focus on the naming of haloalkanes and haloarenes, and we will also understand that what are haloalkanes and haloarenes and how we can name them according to the IUPAC system of nomenclature after looking their structure. The topics that we are going to cover today according to the NCERT, they are first of all our section 6.1, that is classification. Then we will cover our subsection 6.1.1, that is on the basis of number of halogen atoms, basically classification on the basis of number of halogen atoms. Then our next subsection, that is 6.1.2, which is compounds containing sp3 carbon halogen bond. CX means carbon halogen bond. And then we will cover our last subsection today, that is 6.1.3, compounds containing sp2 carbon halogen bond. Let's begin. Let's start with a little introduction first regarding the haloalkanes and the haloarenes. Like, what are the differences between them? What are these haloalkanes? First of all, let's cover haloalkanes because its name is haloalkanes. Halo we use for halogens. So, haloalkanes, the name has halo in it, and alkanes. Right? Alkanes, you know, they are just like carbon structures containing single bond between the carbon and carbon. Halo is denoting the halogens, the group 17 elements, the halogen gases like fluorine, chlorine, bromine, and iodine. Okay. So you can also call them as alkyl halides. Halides again here referring to the halogens, or its representation is by Rx. R where is representing an alkyl group, either methyl, ethyl, okay, and X is representing a halogen bonding with the alkyl carbon, right? So they are formed, the haloalkanes are formed by the replacement of one or more hydrogen atoms in an aliphatic hydrocarbon by halogen atoms. Okay, so how we get haloalkanes? Haloalkanes means mixture of the alkanes and the halogens. So they are formed by the replacement of one or more hydrogen atoms present in our aliphatic hydrocarbon. Aliphatic hydrocarbon means the hydrocarbon containing single bonds between each carbon and carbon, and it is like only containing carbon and hydrogens. Okay, so when you remove either one or more than one hydrogen atoms, when you replace one or more hydrogen atoms from this aliphatic hydrocarbon by replacement by an halogen atom, okay, you remove a hydrogen from the hydrocarbon and you put a halogen at that particular place. Halogen atoms like fluorine, chlorine, bromine, and iodine. Okay, so this is how you will get the haloalkanes. Halogen are attached to the sp3 hybridized carbon because this is we are talking about an aliphatic hydrocarbon. There is singly bonded carbon atoms that are present in the structure. So halogen is going to bind after the removal of one hydrogen from it. Halogen is going to bind with the carbon, which is again a sp3 hybridized carbon. Okay, sp3, because if you see the structure, carbon has tetravalency, right? Carbon can bind through like 4 different bonds. Carbon can bind through 4 bonds, and in the aliphatic hydrocarbon, after the removal or replacement of one or more hydrogen by the halogens, the one of the bond is occupied by halogen, right? So halogen is bonding with carbon with one bond, and the other bonds are occupied by hydrogen and carbon, right? So the carbon is going to have singly bonded atoms around itself. That means the halogen is attaching with the carbon, that is sp3 hybridized. So we have given here an example, like if you take the example of methane molecule. Methane is a gas. CH4 is the formula for the methane. When you remove one of the hydrogen atom from this, or replace one of the hydrogen atom from this by the halogen atom, then you will get a methyl halide, that is CH3X, alkyl halide. Okay, alkyl is methyl halide, X is anything, any halogen atom from chlorine, fluorine, bromine, and iodine. This is how the halogen is going to place at the place of hydrogen in the alkanes to form the alkyl halides, right? And the halogen is going to bond with this carbon. So in this methyl halide structure, the single carbon is going to bond with these 3 hydrogens, and the 4th valency is occupied by this halogen. So halogen is attaching with the carbon, which is sp3 hybridized. Now, if we talk about the other term, that is haloarenes. Haloarenes is basically aryl halides. Okay, haloarenes. Again, halo terms came from the halogens, the group 17 elements, right? And the arenes is we are using for the unsaturated hydrocarbon. Okay, and we can also call it as aryl halides, or you can represent it by AR, single bond X. X is representing the halogens and AR is representing the aromatic ring. How it is going to form? So basically, it is formed by the replacement of one or more hydrogen atoms in an aromatic hydrocarbon by the halogen atom. So in this case, what will happen? Aromatic hydrocarbon. Aromatic hydrocarbon means where carbon, double bond carbon is present in the structure. So in that from that structure, one of the hydrogen is going to be replaced by the halogen atoms, and that's how we will get haloarenes. Halogen here, in this case of haloarenes, attached to a sp2 hybridized carbon. Okay, that means halogen is going to directly attach with the carbon, which is attaching, which is a sp2 hybridized carbon. Okay, so halogen in this case is attaching to a sp2 hybridized carbon. So if you take the example of the aromatic benzene, okay, aromatic ring, that is benzene, formula is C6H6. And when one of the hydrogen atoms is replaced by the halogen in the benzene, you will get halobenzene, that is C6H5X. The hydrogen will be reduced from 6 to 5, and one of the position of hydrogen is occupied by the halogen and forming the bond with the sp2 hybridized carbon, which is double bonded with the another carbon, right? So it is sp2 hybridized because if you see the structure of a benzene is a hexagonal shape structure, right, where each consecutive carbon is having double bond with its successive carbon, right? So like C, double bond C, single bond C, double bond C, single bond C, double bond C. And then this is connected with single bond C with the first carbon. So 6 number of carbons are going to be there in the ring, in the structure, and every carbon consecutive double bonds are present in the structure, right? So when halogen is going to attach with this carbon, so each carbon is undergoing the double bond with the another carbon. Okay, so each carbon, like, it has a tetravalency. Each carbon is having tetravalency. So that means two bonds are occupied by the another carbon. One bond is occupied by the another carbon to form the structure, and one bond is occupied by the hydrogen. But from which hydrogen is replaced by the halogen. Now halogen is at the place of hydrogen, and halogen is directly connected with the carbon, which is forming a double bond with another carbon. So that's why we are saying that here in the case of haloarenes, the halogen is attaching to a sp2 hybridized carbon atom. Let's begin with the classification, that is our section 6.1. First of all, the classification of haloalkanes and haloarenes. Haloalkanes and haloarenes, they are classified into majorly three categories. How? Firstly, on the basis of number of the halogen atoms. So, how many number of halogen atoms is going to be there in the structure of haloalkane and haloarene? This is the first category on the basis of which you can classify these. Second is compounds that containing sp3 carbon halogen bond. Okay. So, the second classification or second category in the classification is the compounds which are containing a sp3 carbon halogen bond. The third category includes the compounds that are containing a sp2 carbon halogen bond, because this is also possible, right? So these are the major three categories in which you can classify the haloalkanes and the haloarenes broadly. Let's talk about our section 6.1.1, that is on the basis of number of halogen atoms. Okay. So in this, monohalogen, dihalogen and trihalogen compounds, what are these? As the name says, mono means single, dia means double, and tri means three, triple, right? And with the mono, there is halogen. With the dia, there is halogen. With the tri, there is halogen. That means one halogen, two halogen, three halogens compound, right? The classification based on the number of halogen atoms, which we are representing by X, present in the structure. Okay, so we are classifying these halogen compounds on the basis of number of halogen atoms that is present in the structure. Mono, dia, tria or polyhalogen compounds are consisting under this. Mono means only one halogen is going to be present in the structure of the compound. Dia means two halogen is going to be present. Tria means three halogen is going to be present. And poly means so many. So many halogens, or you can say more than three halogens are going to be present in a compound. Then we call them as polyhalogen compound. If you see this table here giving three columns in it, first is representing the type, monohalogen, dihalogen and trihalogen. Second is telling us the general structure of the alkane, and third column is telling us the general structure of arene. Arene means where aromatic ring is present, to which the halogen is directly bonded. So if you talk about the alkane first, monohalogen general structure will be C2H5X. It's like an example, okay, where we have this ethyl halide, C2H5X. Dihalogen means we have CH2, and with each carbon we are attaching a halogen atom with it, right? So in this structure of the alkane, we have two number of halogens present which are bonded with the carbon. So it comes under the category of dihalogen. In the trihalogen, the general structure of alkane is X2CH2X. That means here the total 2 plus 1, 3. 3 halogens are present in this structure. That means 3 valencies are occupied by the halogen for the carbon. So this structure is considered as trihalogen compound. Now if you take the case of arene now, where the monohalogen have general structure C6H5X, that is a benzene ring attaching directly with the halogen. Only one halogen is present in the structure, so it is considering under the category monohalogen. Now in the dihalogen, we have C6H4X2. That means we have two number of halogens that are attaching with the aromatic ring. So it comes under dihalogen category. And similarly, the trihalogen have three number of halogens that are present in the structure of the arene. Okay. So this is how you can classify the halogen compounds on the basis of the number of halogen atoms that are present in the structure, either alkane or arene. Let's see some example of haloalkane. So this is a haloalkane, this is a dihaloalkane, and this is a trihaloalkane. So examples of haloalkane on the basis of the number of the halogen atom present in the structure of haloalkane. The first figure is for monohaloalkane. That means the haloalkane is there, right? Halogen and alkane is there, but only one halogen is present. So we are classifying it as monohaloalkane. In the second structure, we have the structure of haloalkane. That means alkane is present, halogen is present, but halogen are in 2 number. Okay, 2x are present, 2 halogens are present. So we are considering it as dihaloalkane. Similarly, the third structure is having 3 number of halogens atoms present in this structure and the alkane or alkyl group. So it is considered as trihaloalkane. Tri is representing 3 number of halogen. Now, let's see similarly the example of haloarenes. So you can see the first structure is representing the monohaloarene, where the halogen is attaching with the benzene ring, the aromatic ring. Okay, so halogen is present, arene, that means aromatic ring is present, and mono we are using because only single halogen is present in the structure. Similarly, if you increase the number of the halogens to 2, then this structure is considered as dihaloarene. And similarly, when the 2 halogens converts to 3 halogens, it is considered as trihaloarene. Okay, so this is how you can classify the haloalkanes and the haloarenes on the number of the halogen atoms that is going to be present in the structure. Let's see our next classification, which is the section 6.1.2, compounds containing sp3 carbon halogen bond. Okay, so now we are going to talk about the compounds that are containing carbon halogen bond, which is sp3 bond. Based on this sp3 carbon halogen bond, it is divided into 3 categories. So bases, like we are already studying a classification, and under this you can again divide it into 3 categories. Okay, the first one is alkyl halide. That means alkyl halides which are containing sp3 carbon halogen bond. Second is allylic halides, which are containing sp3 carbon halogen bonds. Third is benzylic halides, which are again containing sp3 carbon halogen bond. Okay, so under the classification of the compounds containing sp3 carbon halogen bond, we are again dividing it into 3 major categories: the alkyl halides, which includes the alkyl or alkanes and the halogens. Then allylic halides, which includes the unsaturated allylic structure and the halogens. And the benzylic ring, where it includes particularly benzene ring and the halogen. Okay, so let's study or know about them one by one in detail. Let's first cover our topic, alkyl halides. As the name says, it is also known as haloalkanes, right? Because we can do this, right? Alkyl halides can also be known as haloalkanes. So if you are writing somewhere haloalkanes, that doesn't mean that it is not equals to, it will not referring to the alkyl halides. They are same. Halogen atom is bonded to the alkyl group. Alkyl group we are representing here by R. R is any, R can be any group. Methyl group, ethyl group, propyl group, butyl group, any group. Okay. So, halogen atom is bonded to the alkyl group. So, in the alkyl halide, what will happen? We have a halogen, that is X, right? And it is bonding to a alkyl group, that is R, which is a group of alkane. okay, where only single bonded carbon is going to be present. So, form a homologous series with the general formula CnH2n plus 1x. Now, we are just mentioning a general formula of this alkyl halides. So, when you consecutively adding halogens with the different alkyl groups, then you got a homologous series having the general formula CnH2n plus 1 x. N can be any integer 1, 2, 3, 4, 5, 6. Let's say if you put n equals to 1, you will get C1H2 plus 1, that is 3. So CH3x, that means methyl halide. Alkyl halide, that means methyl halide, or you can say haloalkane, that means halomethane. Right? X can be any halogen, fluorine, chlorine, bromine, or iodine. Okay, so you are going to get a homologous series of alkyl halides which are following this general formula CnH2n plus 1 x. You can put any value of n here, 1, 2. If you put 2, what it will be? C2H, 2 times 2 is 4, 4 plus 1 is 5. So C2H5 x. Okay, so you simply have to change the number of, or change the value of n in this general formula. So C2H5x will be ethyl halide. Okay, so when you put different values of this n in this general formula, you will get a homologous series of alkyl halides where the halogen is bonded to the alkyl groups methyl, ethyl, propyl. Classification of alkyl halides. So based on the nature of carbon atom to which the halogen is attached, these are classified further into 3 categories. Now, firstly, we were talking about the sp3 carbon halogen bond compounds. Then in this, we classify them in 3 basic categories: alkyl halide, allyl halide, and benzylic, right? Then alkyl halide again can be classified into 3 categories on the basis of the nature of carbon atom to which the halogen is directly bonded. So, the first category comes primary halide. We also write it as 1 degree. Okay, primary or 1 degree halide. What does it mean? We will see. The second category of classification of alkyl halide is secondary halide or 2 degree halide. Similarly, last one is tertiary halide, that is 3 degree halide. Okay, I hope you know this. Okay, primary, secondary, and tertiary halide, what it refers to. If you don't know, we will see that. So let's talk about the classification of alkyl halide, that is primary, secondary, and tertiary alkyl halide. Let's talk about the primary one first, which is also 1 degree. The halogens that are attached to a carbon which is bonded to only one other carbon. What does it mean? It does mean that when you see the structure of a primary alkyl halide, the halogen is going to attach with the carbon, and that carbon is only going to attach with only one another carbon. Okay, so at the same time, the carbon having halogen bond binding to it is bonding to only one another carbon. Then it is considered as a primary alkyl halide. For example, CH3CH2X, where X is representing the halogen and CH3CH2 is ethyl, ethyl group. But here, if you see the structure, halogen is attaching with this carbon, right? And this carbon is only attaching with one carbon, right? So this is considered as a primary alkyl halide. So you can call it as primary ethyl halide. Okay, you will understand more when you see the secondary and tertiary alkyl halide. So this is the structure of primary halide, primary alkyl halide, where this is the carbon. We are only talking about the carbon which is bonding with the halogen. Okay, so this is the carbon which is bonding with this green halogen, and it is also bonding with 2 hydrogens, but it is only bonding with one of the carbon from this R prime alkyl group, right? So the carbon which is bonding with halogen is bonding with only one carbon from this alkyl group. So this is a primary alkyl halide. You can call it as 1 degree, and you can relate it with that carbon is attaching with only one carbon. Okay, halogen carbon, or you can say halogen is attaching with the carbon and that carbon is only binding with one carbon, bonding with one carbon. Then it is a 1 degree or primary halides, alkyl halides. Let's understand about the secondary alkyl halides representing by 2 degree. Halogen which are attached to carbon which is bonded to 2 other carbons, because we are talking about 2 degree. 2 degree means now the carbon which is having halogen, that carbon is going to bind with 2 different, or you can say 2 carbons, 2 carbon atoms. Okay, so the halogen is attaching with the carbon and that carbon is bonded to 2 other carbons. Then the alkyl halide you got is secondary, is 2 degree. For example, CH3 whole twice CHX. What it is saying? That this halogen X is bonding with this carbon and this carbon is bonding with 2 methyl groups. That's why we are writing at CH3 whole twice. That means carbon-carbon bond will be there between the methyl group and this carbon, right? So the halogen is bonded with the carbon which is bonding with 2 carbon atoms. So this is considered as a secondary or 2 degree alkyl halide. This is the figure for that. You see that halogen is bonding with this carbon and this carbon is bonding with 2 alkyl groups, R prime and R double prime. Okay, R prime and R double prime can be same and cannot be same, may be same or may not be same. Okay, so but the fact is we are only observing the fact that carbon is bonding with halogen and also the same carbon is bonding with other 2 carbons more, right? So this structure is considered as secondary alkyl halide. You can learn this by 2 degree because the carbon which is bonding to halogen is bonding to other 2 carbon also. So it is a 2 degree alkyl halide or secondary alkyl halide. Now comes the third category, that is tertiary, like 3 degree. Okay. Similarly, the same pattern, that halogen is attaching with the carbon which is bonding with 3 other carbons, because carbon can bind to 4 different atoms, right? Because it has tetravalency. Now, carbon is attaching with first valency is occupied by halogen already. Remaining 3 is occupied by another carbons. Okay, other carbons. So, in that case, you will get a tertiary alkyl halide. For example, CH3 whole thrice CX. So, this halogen is attaching with this carbon which is bonding with 3 other carbons of methyl group. So this structure is a tertiary alkyl halide. Again this diagram. So you can see that halogen is attaching with the carbon and this carbon is attaching with 3 other alkyl groups, R prime, R double prime and R triple prime. This R prime, R double prime, R triple prime may or may not be same. You can just focus on the fact that the carbon bonding with the halogen is also bonding with 3 other carbons of alkyl group. So this is 3 degree alkyl halide or tertiary alkyl halide. There is a note. Note is that R prime, R double prime, R triple prime are alkyl groups. Okay. So the R prime, R double prime or R triple prime we are using in this structure, they are actually representing alkyl groups as I said, and they may or may not be same. Now, let's see the other classification of our sp3 carbon halogen bond, that is allylic and benzylic halides. Let's first talk about the allylic halides. Allylic halides have halogen atom which is bonded to a sp3 hybridized carbon atom which is next to a carbon-carbon double bond or sp2 hybridized carbon. Okay, try to understand. What I am saying that halogen atom is bonded to a sp3 carbon atom. Okay, but that sp3 carbon atom is attaching to a carbon-carbon double bond or sp2 hybridized carbon. Then the structure or then the compound you got is known as allylic halides. You will understand more by looking at these diagrams. The first is representing the CH2X, and this CH2 is bonding with this carbon, having one hydrogen, and other than that having single bond with CH2 and double bond with another CH2, right? So this carbon here is a allylic carbon. Why? Because this carbon is attaching with halogen directly, or you can alternatively say that halogen is attaching with the carbon, which is attaching with the carbon that is double bond, or that is making double bond with another carbon. Okay, so the carbon at which halogen is bonding, that is sp3. Okay, but that carbon is bonding with the double bond, or carbon-carbon double bond. So that's why we are calling it as allylic halide. And this carbon which is bonding with the C double bond C and also halogen, this is also known as allylic carbon. Okay, similarly you can see this another diagram where we have this halogen representation by X. It is bonding with the carbon. Okay, don't confuse with the ring. It is not a benzene ring, right? In the benzene ring there is consecutive double bonds present. There is only one here, there is only one double bond present, so it is not a benzene ring. So halogen is attaching with the carbon, and this carbon is attaching with the C double bond C. That means the carbon which is making double bond, right? So this is also allylic halide, and this carbon where the halogen is attached is known as allylic carbon. Okay, we talk about hybridization. Halogen atom is attached with a carbon which is sp3 hybridized. It has tetravalency. 2 are occupied by hydrogen, 1 is occupied by carbon, and 1 is by halogen. But this sp3 hybridized carbon atom is bonding with the carbon which is making double bond with another carbon, that is sp2 hybridized carbon. Okay, so this is a allylic halide, and this carbon to which halogen is bonded is allylic carbon. So this is an example: CH2 double bond CH, single bond CH2, single bond CH. Okay, this is an example of allylic halide. How? This chlorine is a halogen and it is attaching with this green colored carbon, and this is a sp3 hybridized carbon. But this sp3 hybridized carbon is bonding with this carbon which is making double bond with another carbon. Okay, so here this green color carbon is a allylic carbon. Okay, and this is example of allylic halide. Now let's talk about the third category, that is benzylic halide. As the name says, it includes benzene. Halogen atom here is bonded to an sp3 hybridized carbon atom which is next to an aromatic. It is simple, right? So still don't forget that still we are talking under the category of compounds containing sp3 carbon halogen. Okay? So in the benzylic halides, the halogen is attached or is bonded to a sp3 hybridized carbon atom, and that carbon atom is directly bonded to a aromatic ring, and it can form primary, secondary or tertiary structure. Like this structure where halogen is bonding with this CH2 which is sp3 hybridized, because it doesn't forming any double bond. Okay, so halogen is attaching with this carbon, sp3 hybridized carbon, but this carbon is directly attaching with the aromatic ring. Okay, so this is a benzylic halide and also a primary benzylic halide, right? Why? Because halogen here, the primary concept will be same. We are focusing on the halide here, right? So we only see that how the halogen is going to attach with the carbon and how that carbon is going to bond with another atoms. Okay, that is going to that is going to tell us whether it is primary, secondary or tertiary. So here the halogen is attaching with the carbon, and this carbon is attaching with only one carbon. So this is the primary benzylic halide. Similarly, you can see this other diagram where the halogen is attaching with here there is a presence of carbon here at this dot. Okay, so halogen is attaching with carbon, and this carbon is attaching with R prime alkyl group and R double prime alkyl group, After fulfilling its 3 valencies, then its 4 valencies fulfilled by this aromatic ring. Okay, so halogen is attaching with carbon, and this carbon is directly attaching with aromatic ring. So it comes under benzylic halide. Now, if you talk about secondary or tertiary, if R prime is a CH3 methyl group and R double prime is a hydrogen, so that means this carbon at which halogen is bonded, it is bonded to 2 carbons. This R prime methyl group carbon and this aromatic group carbon. So it is a secondary benzylic halide. But if R prime and R double prime both are methyls, that means halogen is bonded to a carbon which is bonded to 2 other or you can say 3 other carbons, which is one from the methyl R prime and one from the R double prime methyl and one from this aromatic ring carbon, right? So this carbon at which the halogen is bonded, this is again bonding with 3 other carbons. So this is considered as tertiary benzylic halides. Okay, so this is the classification of allylic and the benzylic halides, or the compounds which are containing sp3 carbon halogen bond. Now, let's move to our next subsection, that is 6.1.3, compounds containing sp2 carbon halogen bond. Okay, sp2 carbon halogen bond means the carbon here is going to be sp2. Okay, so let's see those compounds. Now, based on the sp2 carbon halogen bond, it is divided into 2 categories. So now this classification is divided again into the 2 categories. First is called as vinylic halides and second is aryl halides. Okay, remember the name, they are important. Vinylic halides and aryl halides, where we have sp2 carbon halogen bond. So let's talk about these in detail, vinylic and aryl halides. Let's first talk about the vinylic halides. So halogen atom in this is bonded directly to one of the carbon atoms of carbon-carbon double bond. Okay, basically you are saying that halogen atom is directly bonded to a sp2 hybridized carbon atom. Okay, so halogen atom is bonded directly to the carbon atom of, or you can say one of carbon atom of carbon-carbon double bond. Okay, so this is considered as vinylic halide. That means halogen atom is bonded with the sp2 carbon atom, and that carbon atom is double bonded with another carbon. You can see the diagram. This is representing vinylic halides, where halogen is directly bonding with one of the carbon of carbon-carbon double bond. Similarly, in this case, halogen is bonding with this carbon, which is one of the carbon from carbon-carbon double bond, right? So this is vinylic halide. So halogen is bonded to sp2 hybridized carbon. The example is CH2 double bond CH single bond Cl. Here if you notice, the chlorine is a halogen and it is attaching with this carbon, which is forming a double bond with CH2. So you can say that chlorine is attaching with a sp2 hybridized carbon, or one of the carbon atom of carbon-carbon double bond. So this is the example of vinylic halide. This is actually you can say vinylic halide, right? Halide is here, or halogen is here, chlorine. Second category is aryl halides. So aryl, aromatic, right? So halogen atom here is bonded directly to a sp2 hybridized carbon atom of an aromatic ring. Now the aryl halides is that halogen is going to directly bonded to a aromatic ring. Then you will get a aryl halide. So you can see the diagram. Here halogen is directly bonding to a aromatic ring, and this carbon is making a double bond with another carbon. That means it is sp2 hybridized, and this structure is aryl halide. Similarly, this second structure is also considered as aryl halide. The halogen is directly bonding with the aromatic ring, or you can say substituted aromatic ring with methyl. So, but the important thing is halogen is bonding with the one of carbon atom of a carbon-carbon double bond. So this is a aryl halide. Aromatic ring is present in it. Okay. The example for this includes C6H5Cl, okay, chlorobenzene. So there is benzene ring directly attaching with chlorine. This is an example of aryl halide. The chlorine is bonding to a sp2 hybridized carbon atom of aromatic ring. Okay, so let's see the summary. So what we have covered today. First of all, we have talked about haloalkanes, right? Haloalkanes form after the replacement of one hydrogen atom or more hydrogen atoms of the aliphatic hydrocarbon by the halogens atom like fluorine, chlorine, bromine, and iodine. Right? Example includes CH3Br, methyl bromide, where bromine is halogen and this methyl group is alkyl group. So it is forming a haloalkane. Okay. So after the replacement of one or more hydrogen atom of the aliphatic hydrocarbon by the halogen is going to form us or it's going to give us a haloalkane or alkyl halide. Then we have focused on haloarenes. What is haloarene? So it forms after the replacement of one hydrogen atom of aromatic hydrocarbon by the halogen. For example, C6H5 bromine, bromobenzene, right? So when in the aromatic ring, one of the halogen is replaced by the halogen, then you got a haloarene or aryl halide. Then we have covered the classification. Firstly, on the basis of number of halogen atoms present, okay, in which we classify them as mono, dia, or tria, and poly, right? So alkyl and aryl halides are classified as mono, dia, or poly halogen compounds based on the number of halogen atoms present in the structure. Like mono has only single halogen in the structure, dia has two halogen in the structure, polyhalogen has many more, like more than two halogens present in the structure of the compound. So we are considering them as mono, dia, or polyhalogen compounds of alkyl and aryl halides. Example we have seen like this is representing the mono haloalkane where bromine is attaching with CH2 and CH3, right? CH2 is attaching with CH3. So in the structure, only one bromine is present, one halogen is present, so it is monohaloalkane. In this second structure, we have dihaloalkane where two bromines are present in the structure, and in this third structure, we have four bromines are present, that is more than two. So we are considering it or we are calling it as polyhaloalkane. Then we have talked about the classification of compounds containing sp3 carbon halogen bond. Alkyl halides are further classified into primary, secondary, tertiary, or you can say 1 degree, 2 degree, or 3 degree according to the nature of the carbon to which the halogen is bonded directly. Okay. So in this classification of sp3 carbon halogen bond, we have talked about the alkyl halide, which are further classified into the primary, secondary, or tertiary halide. You can see that in the first diagram, we have a primary halide diagram where bromine is attaching with this carbon having a star. That means this carbon is only bonded with one carbon. Okay, we are going to judge this structure name on the basis of the star carbon because this is attaching with bromine. So bromine is attaching with this carbon, which is only attaching with one carbon. So this is a primary halide. If the bromine is attaching with the star carbon and that star carbon is bonding with other two carbon atoms, then we are considering or we are calling it as secondary or 2 degree halide. Similarly, if the star carbon at which the bromine is bonded to another 3 carbons, okay, then we are calling it as tertiary halide. We can't have more than this, like we can't call it as quaternary halide. Why? Because carbon can only bonded to the 4 different atoms or same atoms because it has tetravalency, and one of the halogen is also important to attach to it because then we are going to call it as alkyl halide, right? So bromine is attaching with this star carbon, and this carbon is going to decide the name. This carbon is attaching with the other 3 carbons, that means it is going to be tertiary halide. Then we talked about allylic halides, which are the compounds in which halogen is bonded to a allylic carbon. That means Allylic carbon means the carbon which is sp3 hybridized but it is attaching with a sp2 hybridized carbon. Okay. Then we talked about benzylic halides, which are the compounds in which the halogen is bonded to benzylic carbon or the carbon of, you can say the carbon which is sp3 hybridized and that carbon is directly bonded to a benzene ring. Then we are calling them as benzylic halide, right? So we are studying or we have studied alkyl halide, allylic halide and benzylic halide under the classification of sp3 compounds, or you can say compounds containing sp3 carbon halogen bond. Okay, so allylic halide, halogen is going to be present with the is going to be bond with the sp3 hybridized carbon, but that carbon is going to bond with sp2 hybridized carbon. Here similarly in the benzylic halide, halogen is going to bond with the sp3 hybridized carbon, but that carbon is going to bond with benzene ring. So we are calling it benzylic halide. Okay, and the carbon that we are talking about, the sp3 carbon to which halogen is bonding, in the allylic halide case we are calling them as allylic carbon, and in the benzylic halide case we are calling them as benzylic carbon. You can see this is a allylic halide because bromine is attaching with this carbon which is sp3, but this carbon is attaching with the sp2 carbon. Similarly benzylic halide, where bromine is attaching with the sp3 carbon, but this carbon is attaching with a benzene ring. Then we have talked about the topic of classification of compounds containing a sp2 carbon halogen bond. Here, in this case, we have talked about the vinylic halides, which are the compounds that are formed in which halogen is bonded to a carbon double bond carbon. Okay, so halogen is directly bonded with the carbon double bond carbon. Okay, one of the carbon atoms of carbon double bond carbon. Aryl halides, then we talked about, which are the compounds in which halogen is attached to a sp2 hybridized carbon of aromatic ring, of benzene ring. Okay, so aryl halides are the compounds where halogen is directly attached to sp2 hybridized carbon of aromatic ring. You can see this is the vinylic halide diagram where bromine is attaching with one of the carbon of carbon-carbon double bond, and this is aryl halide because here bromine is attaching with sp2 hybridized carbon of aromatic ring. So these are the major topics that we have covered today in our lecture. Okay, thank you so much. That's all for today's chemistry session. Thank you.